Okay, some important announcement first. For your lab test 1 marks, I do realize there is some issue there. So there are 2 ways you can check your marks. You can either go to ePost. Apparently, I got some problem with the ePost. I'll try to fix it after class. On the other hand, you can just go for the feedback command. I believe that one is already working. You can see exactly your marks the same. I just checked it actually right before the class. Yeah, so for the feedback, you can definitely try that. But for the ePost, I'll just drop by the lab session today, make sure everybody can see it. Okay, now important over here for lab test 2, originally scheduled for next Monday, right? So I discussed with other instructor for other sections, we decided to postpone that for 1 week. Okay, hopefully that can be relieved, but I'll give you a study guide hopefully soon. It's going to be Monday, November 5th. Not next Monday, but the Monday after. Okay? And there will be some formal Moodle announcement in a bit. Okay? You mean the lab test 2? You mean how long it will take, or the study guide? I'll try to give that to you hopefully by the end of Friday. I'll try to. Okay. Yeah, you get at least one week to prepare. Okay. And I would like to share some statistics with you for lab test 1, okay? Especially for the programming part. Guys, please, okay? So for the lab test 1 programming, okay, so how many percent actually got 100 marks? How many percent? Turns out to be 18.98% who got 100. And how many percent who got A and A pluses? Altogether, we got 33.47% who got A or A pluses. Okay, and the next part would not be very pleasant for those of you who got it, but don't worry, just if you need help, let me know. How many actually got E or F? 33.58%. I would say, once you see the programming part for your lab test 1, if you do fall between the E and F range, do talk to me as soon as you can. We'll see how we can improve you for lab test 2 and 3. Okay? You can see many people succeeded in lab test 1, but many of you also did not do so well. I hope to help, but drop by if you need to talk. Okay. I'd like to do one more thing, right? I believe almost everybody I want to present is today here. Remember the card trick example I did before the reading week? So far, 5 of you guys actually came to me and present your solution. 5 of you. I would like to present just a very small prize to those people there in the class. Okay? Wilson, is Wilson here? So he might be the only person we'll miss today. Anyway, so just got some small prizes over here. So Jordan, come to the front. So he is the first one who solved the problem. I think just after a few days, right? Yeah, maybe.
So the lecture was Thursday and I
Wednesday,
Friday.
And then you got it Friday. Yeah. All right, there you go. That's for you.
Thank you.
You're welcome. Okay, open that later. Okay. And I got. He's the first one, and then for all the other 4, I'll give the same. So you got yours is a little bit bigger for the first one. Wilson's not here. Too bad. I'll give that to him later. So Jordan, come on, and you come on first, and one more. Where is that girl? Where are you? I remember I saw her. Oh, here you go. Come to the front. All right, there we go.
Thank you very much.
You're welcome.
Appreciate it.
All right, there you go. Ring. I got it. All right. Oh, nothing important. All right. So guys, I would say if you still want to try the card trick, feel free to present your solution to me. I'll try to give you some candy if you present it to me. All right? Okay. Wilson is not here, yeah, right? Are you Wilson? You solved the card trick, right?
Yes, I do.
That's a prize for you.
All right, thank you.
All right. Good. All right, guys, let's get started, okay, with the course contents. All right. So what I would like to start with is the sorting that we talked about last Wednesday. Basically, we got two kinds of sorting we talked about. Let me review very, very quickly about conceptually how they work differently. They work almost symmetrically, I would say. And let's review how we figure out their running time. And what I would do is I would like to go over also their implementation with you. That could be a very nice case study for both the asymptotic analysis, also for complicated computations. So we'll do both, okay? And then move on to other new topics. Okay, so for sorting, the way to understand selection sort and insertion sort, visually speaking, is to think about initially, you start with any arbitrary size array where everything is unsorted. I use the pink to say everything is unsorted, right? Eventually, the output should be an array that is everything is sorted. That's why it's all green, from all pink to all green. And the idea is for every kind of iteration you want to have conceptually, for every step, you want to just increase the size of the green region by just one. So after the first step, the green region has just one element. After the second step, you got two elements. And after the n step, you got exactly n elements. Okay? That's the same idea for both selection sort and insertion sort, just the same idea. But now what's really the difference? The difference is really about how you complete each step and how you grow the green area by one element. In the case of the selection sort, the way you grow the green area is by selecting the minimum elements from the pink area and then put it in the green. Okay? And the way you grow the green area for insertion sort is simply pick the leftmost elements in the pink area and then insert it to the right spot, the correct spot in the red area, in the green area. Okay, so that's the difference. But now let's think about, given we understand conceptually how each of the sorting works, so how do we figure out their running time intuitively? As you can see, again, since we're doing asymptotic analysis on the paper, we don't necessarily have to see the Java code before we can judge. So that's really the advantage for doing such thing on the paper. Now, in the case of selection sort, if you talk about the very first step over here, what we're doing is we're going to select the minimum from the entire red area. In that case, it will be linear, agree? Because the worst case will be maybe the minimum is simply at the end of the array. So I'll just put n over here. So that's for the first step. What about the first step for insertion sort? It's kind of symmetric, which means we want to grow the green area just by one element, and we simply pick the leftmost element from the red area for insertion sort, and then insert it. In the first step, it's trivial, because the green area is simply just empty, just insert it. So as opposed to n, you'll be 1. You can see the critical difference, right, between the two. Okay? The first step for the selection sort is the most expensive, whereas the first step for insertion sort is the cheapest. Okay. Now let's see the second step again. For the second step, basically we are facing this red area over here with n-1 elements. In that case, for selection sort, how do you select the minimum from the n-1 subarray? Well, you will take n-1 step, iterations, maximum. So that'll be n-1 for the second step. And now what about insertion sort for the second step? Basically, as a result from the first step, you already have a green area of one single element. So now for the second step, you have to make a choice between insert it over here or insert it over here. Two choices, right? So that's why conceptually it will be 2 as opposed to n-1. Okay, so far so good between the difference. If you go on with this pattern over here, let's talk about the second last step for each sort. For the second last, basically we start with something like this. This is what we start with. And this is what we want to end up with. So basically, how many elements do you have to select for the minimum for the selection sort? Well, you just have 2 over here, just 2 red elements. In which case, I'll just put 2 here. And now, what about to insert? To insert, it depends on the size of the green area, right? If the size of the gray area is 2, what about the green area? It should be n-2. Right? Because the size of the input is simply n, so n-2. That's why it would take about n-2 insertion to actually insert into the right spot. Okay, finally, you just decrease to n1 and then n-1. Okay, that's kind of the idea. So now you can see that although each step is quite different between the insertion sort and selection sort. Yes?
In the very first one, you had n
Yeah.
and 1. Why is it not n-1?
Sure. The question was, for the first step for selection, so why is it n rather than n minus 1, right? Remember the size of the array we are talking about in general simply of size n. So that means the size of the array over here, n. How do you choose n elements and get the minimum? The worst case, you have to inspect every element over there and find out the minimum, right? So that's why it's n. Okay, yeah. Okay, so now, although each step individually is quite different between the two sorting, but when you aggregate all the steps together, it turns out to be the same. So now, as we said before, this is the series you should know, hopefully from the high school, right? How do you add up n numbers from n down to 1? So, right, the front plus the end, multiply how many turns? We got n turns divided by 2. Okay. Similarly, also the front plus the end, and then how many turns we have? We got n minus 1 turn. And then divided by 2. So that's the exact, more or less like exact number of primitive operation we have to perform. But how do we get the asymptotic bound? As we said before, you can simply drop the lower terms and drop the multiplicative constant. So this is simply big O of n squared. Because you can see n times n will give you n squared, that's highest power. Everything else can be dropped. Similarly, you can n times n will be n squared, everything else can be dropped. So this is also big O of n squared. So that means for selection sort, insertion sort, both of them are quadratic. Okay, it's a quick review of what we said last Wednesday, conceptually, before we see the code. I would say everybody got different style. You might prefer learning about the conceptual ideas at a more abstract level before you see the code. I personally prefer that. Maybe it's also better for you to learn the first. But some people might prefer seeing the code first to actually see exactly it works in the concrete step. But you can try both. Okay, if no questions, I will go on to the code. The selection sort is a little bit easier to understand for the insertion sort. So I'll go for selection sort first. Okay, you can also see the code on your slides, and also I made the source code available for you with some JUnit tests, so you can try them out. I do have some small exercise for you at the end. Okay, so this is our selection sort over here. It's a Java method, and then we have array A, and also input size is n. N is simply A.length, okay, for redundancy. So now let's try to understand exactly how things work. Okay, let's understand also the code from the big picture. Apparently, we have two loop counters over here. We got loop counter I, and also we got loop counter J, first of all. We got two loop counters to manipulate. You can think about loop counter I starting from 0 until n minus 2. Okay, it works a little bit like this. You can think about I is equal to 0 tells you where the green area should start. Initially, we want the green area to start with index 0. That's where we want to grow. That's why after the first step, this index should be the green elements. Okay? So that's so I would be the start, actually the green area, which means it's sorted area. Okay, what about J? Let's try to trace it a little bit and see what happened. Again, let's see. We got this example here. We got array A. We got 3, 1, 4, 2. Okay? Now, let's have a look. What I would do is, let's say, I start with the value of, for the very first iteration, I'm going to use green, and then use different color for each iteration. For the very first iteration, I will be simply 0. Hopefully you agree. And then we have something called minimum index. Remember, each step for the selection sort, we have to find out the minimum. So whatever index for that minimum number should be the min index. Okay? So we'll get there in just a moment. And then we also have this nested for loop over here. And then we're going to have J starting from I. At this point, I is simply just 0 for the first iteration. And then J is less than or equal to n minus 1. And we know that for our purpose, A, which is the array of size 4. So n is 4. Okay? So that means J is going to be from 0 until 4 minus 1, which will be 3. Agree? Okay? So that means J is going to be from 0, 1, 2, and 3. So these will be the values for J. Okay? And then I'm going to make it a little bit faster for you. Let's do a little bit fast motion. So this loop, inner loop over here, you can see it's just doing to see where the minimum index is. We're just finding out the minimum. You know that pretty well from 1022. Okay? So now let's say this. In the very first iteration, I is over here. This is I. And j is going to be from 0, 1, 2, and 3, basically, right? And then we're going to find out what the minimum index is. Can you see what the minimum index is? Not the value, the minimum index. What's the minimum? Well, apparently, you see the minimum value is 1 over here, right? So that means the minimum index for that particular value is 1. That's the minimum index. Okay? That is the minimum index for the very first iteration. Okay, so at this point over here, minimum index will just be 1. So now I want you to look at these 3 lines of code over here. Can you see what it's trying to do? I heard swap. Swap what with what? What with what? Well, we know that this is the current value for I, and this is the value for minimum index. Basically, since we know that whatever that is stored at index 1 is a minimum value, we want to swap that with what we are currently pointing at for the green area, basically. Okay? If you do the swap, what's going to happen? That means 1 is going to become over here, and 3 is going to become over here. Okay? Let's just draw it down. So minimum index at line number 6. At this point, we know that minimum index will just be 1. And then we know that A1 is simply equal to just 1. Okay? It just happens to be 1 over here. And now we want to know, after the swap over here, let me just do it for the first time. What's going to happen here? Basically, what we have is the temp is going to store the value for A0. I is 0. And then A0 is going to be rewritten by A with the minimum index, which is 1. And then A at position 1 is also going to be assigned to whatever value this is, right? And what's this value over here? It's simply just 3. Agree? So that would just be 3. I'll put 3 here. Okay? So now what's going to happen afterwards? Let's draw the array very quickly. Afterwards, what A will become is something like this. Okay? Size doesn't change. And then 4 and 2, they are unaffected. What we have done was we swapped the value between 3 and 1. So 1 is here, 3 is here. And let's link it back to where we were in the conceptual level. That means over here, 1 is the only one that's sorted, whereas the other ones are unsorted. That's what we have done for the very first iteration for the outer loop. Okay? So J is used to find out where the minimum value is, to find its index. And I, the outer loop, is going to tell you where the end of the green area is. Okay? Let's do one more iteration, and hopefully you'll get. Yes?
So n is going to be the size of the array?
Correct. Think about how you're going to call this method here. The question is, what's n? The reason that I put this kind of extra parameter over here, just to show you, to see more clearly when you do the analysis. Okay? So the way you call this method over here would be, you'll say selection sort, and then you would say A over here, and then A.length. That's how you would call that. Okay? Good. Let's do one more iteration, and then hopefully you'll get an idea to go all the way to the end. Yes, go ahead.
Can you explain one more time how you get the minimum index?
Sure, no problem. So the way you get a minimum index is by executing line number 4 and 5. Okay? If you look at line number 4 and 5, it's basically to say whatever the current value for I is, in this case, it's 0, right? So that means we're going to scan through the array from index 0 until the end, because until the end, right? And then we'll find out what that minimum value is. You can see every time, if the current value we are looking at is strictly smaller than the minimum so far, basically, right? If that's the case, we'll reassign the minimum index to be j, right? So the worst case apparently is the minimum is basically at the end of the array. Okay? So that's a critical step, right? As you can see again, why the very first step for the selection sort is the most expensive. Because for the very first time, you had to scan through from this index here all the way to the end. But for the second iteration, you're going to start with this index over here and scan all the way to the end. You got one element less to actually scan through. That's why it's cheaper. Okay? Why don't we do one more? Okay, let's do one more. I'm going to use red. Okay, so now let's say we are done with this, and then we go all the way back to the beginning of the outer loop. So we know that I is going to be incremented from 0 to 1. Okay, so I is going to be 1. And then what we're going to have is, and I is going to, again, go all the way to the end. And what about the minimum index over here? Okay, let's see over here. So j is going to be starting from I being 1. So that means we're going to start with this element over here. That means we're going to ignore the element that's already sorted at index 0. You can see the change over here. Okay? And then if we try to do this, let's say j is going to be 1, 2, and 3, starting with 1 and all the way to the end of the array. And now, if you think about it, if j starts from here, and what's going to be the minimum index at the end? Minimum index, not minimum value. 3, right? Because we're talking about this as being the minimum. Okay, so minimum index will be 3, and A3 is basically the value of 2. Okay, so now we're going to execute this fragment of code against line number 6, 7, and 8. How do we do that? Again, we'll do a swap. Okay, now conceptually, basically we know that this is the minimum index we have, and this guy over here is the j. Oh, sorry, I that we're talking about. Is the I that we talk about, which is 1. So now how do we swap them? The way we swap them is by executing this block of code. After that, what do we have? Let's have a look. Let me draw the array again. Basically like that. 1 remains unchanged. And then we swap these two elements over here. So that means 2 becomes over here, and 3 becomes over here, and 4 remains unchanged. So what we have done after the second iteration is as follows. So we got 1 and 2 being sorted, whereas the red area has been reduced by size 1. Okay, we keep going until we execute everything, and we should get everything being green. So that's selection sort. Okay, I will leave that as exercise for you to go until the end of the algorithm to let it terminate. Apparently, you need 2 more iterations to complete it, right? I'll leave the rest to you. Any question about the code over here? Okay. Of course, you don't memorize it. I would say a very good practice for you is as follows. You simply review what is going on conceptually and just write a method yourself. Think about how you can translate the abstract idea into concrete code. That's really the technique you want. Okay? Because every time you're dealing with new problem, all you can have initially is some abstract idea. How you express the solution using Java code, it takes some experience. Okay? Okay, are we ready for insertion sort? Yes, questions?
Line 6, 7, 8.
Yep.
Doesn't that?
You want me, are you comfortable with the line number 6, 7, and 8 being a swap program?
Wait, I'm confused. Does it like execute on every iteration, or is it just?
Oh, yeah, it is executed at every iteration. More specifically, actually, when you download the code, it will be clearer. For here, for presentation, I just use the indentation to indicate. But you can think about this block of code over here. This block over here is simply outside the inner loop. It's outside. That's why it's in parallel. Which means every time after you execute a particular nested loop, you will figure out the minimum index. That's why you do the swap. Okay? Okay, guys, any questions? Yes? It will not influence the result. That's a good question. The question was, what if we got duplicates in the array? For example, if you simply got 4, 4, 4, 4. If you run it just by running this, that means the first time you choose the minimum being 4. Second time, choose the minimum being 4. Third time, choose the minimum being 4. It will still work. Yeah. Okay, let's have a look at insertion sort, which is slightly trickier. The trickier thing about insertion sort is the way I pick one. Well, let me say one more thing. The way I pick an element from the red area is by figuring out the minimum index, right? That's why it's a little bit expensive. But now, the way I pick one element from the red area is simply by picking up the leftmost elements from the red area. And then now, in order for me to grow the green area for insertion sort, that's the tricky part. I have to insert it in just the right spot. Okay? Let's do one exercise together before we see the code. How about that? Very quick exercise. Let's say the following. Okay? Let's say if I have an already sorted array, let's say we already got, let's say 2, 4, and 8. Okay, let's say this is a green area. Okay, I want you to think about two scenarios, two. The way to think about this, let's say if I say insert, let's consider different cases. If I say insert 9, okay, so now I got 0, I got 1, I got 2, okay? Of course, the array also got empty slots over here, so we can put it. How do I insert the element 9? Where should I put it? Index 3. Given that the array is already sorted, if the element I'm trying to insert into is already larger than or equal to the maximum, which is the rightmost in the green area, then I can just insert it right away. Okay, that's one case. Okay, let's try the second case. What if I got insert and then I got, what about 3? Okay, so now how do I do it? Basically, you have to scan through the green area from right to left, basically, right? So imagine that how you would do this in Java. You have to start a loop counter with some value and decrement it each time, right? Basically, I'm going this way here. Going this way here. The first element I encounter will be of value 8. And 3 is not strictly larger than 8. So this is not the place to insert. Okay? And when I see that 4 over here, 3 is also not strictly larger than that, so it's not a place to insert. And when I see this guy over here, 3 is strictly larger than 2. So that means I should insert it over here, conceptually, right? And how do I insert into it? That's the thing. Remember some little exercise we did when we talk about array? If you want to insert into index I, you have to shift everything that's on index I and to the right of index I to the right by 1 position, right? And then put it there. Okay, that's something we learned about before we even talk about sorting. So that's something fundamental you should know. Okay, I'll just mention that quickly, and then you'll see exactly that in the code. Basically, this part of the code tells you about how to shift. But I'll show it to you in just a moment. Okay, one more case. What about if I have insert, what about just 1? So now, where should I insert it into? Well, index 0, don't you agree? In that case, because I basically can see 1 over here is not larger than or equal to that. 1 is also not larger than or equal to this element here. 1 is also not larger than or equal to this. But I'm reaching the end. So that means 1 is going to be the smallest element for the new green area. Okay? So these are the 3 cases you have to understand in order to write the Java code. Either insert right to the end of the green area if that happens to be the maximum. To insert it somewhere in the middle as soon as the element is larger than or equal to the current one you're looking at. Or you have to insert all the way to the end if that happens to be the minimum. Okay, so these are the 3 cases. Let's have a look. Again, we have a nested loop. But the interesting thing about this, you rarely see a nested for and while. So that's why it's kind of interesting to see. Okay? But according to what we learned from 1022, while loop and for loop, they are completely equivalent. So you can definitely rewrite this while loop as using a for loop. I'll leave that to you. If you got trouble, let me know. Okay, but let's just go on with the story. Okay, let's again, for the very first iteration, I is going to be 1. Okay, and then n at the moment is simply just a.length, which will be 4. And then let's have a look. Let's I will be 1, and we have something called a current value. Current value is basically the value we want to insert into the green array, the green area. Okay. Initially, of course, everything is unsorted. Initially, you can think about it like that. Initially. Okay. So now the current value is simply A at position I, which is A1, which is 1. Okay, so far so good. And then what about J? J over here, J is going to start with the value of I, which is 1. Okay, so far so good. That means J is going to start with over here. This is where J is going to start with, and then we basically go backwards to see where the right spot is to insert. Okay, and now let's have a look at the while loop over here. This is part of the exercise I would like you to really convince yourself. Somehow you want to convince yourself this stay condition over here, stay. That means as long as this condition over here is true, you're going to stay and execute the body of the loop one time after another time. So now, one thing to think about to convince yourself this state condition is right, think about what's the logical negation of that. That's something we did back in 1022. Why don't we do that very quickly? Okay. So I pose the following question to you already here. Okay, this is the while loop we talk about. Think about this question. Under what condition does the while loop exit? Intuitively, you should exit from the while loop if the state condition becomes false. How many possible ways can you make it false? Given that it's a conjunction. Huh. I heard 3. Are you sure? Okay, I should make my question a bit more carefully, okay? So let's say this. J larger than, okay, let me just do this maybe in the next slides so you're okay with that, the logic. Okay, let me just copy that very quickly. J larger than 0 and over here, A, J minus 1 larger than current. Yep, something like that, yeah. So this is the while condition to stay. And now you will exit. Remember what we talked about De Morgan. If some of you actually is taking 1019, maybe you're learning this. But anyway, this is the only logical law that we learned from 1022. Let's try that together, okay? You will exit when it is not the case that this condition is true, right? So that means not the case, J larger than 0 and A, J minus 1 larger than currents. We exit from the while loop when the state condition is not the case, right? And we can simplify this a little bit further, right? We can distribute the negation over here over and turn the conjunction into disjunction, right? Okay, it's something called De Morgan. So this is equivalent to J less than or equal to 0, the negation of that. Or A, J minus 1 less than or equal to the currents. So this should sound a little bit more familiar to how I described the algorithm in the previous slide, right? So what does that mean? That means we're going to exit from the loop simply means we know where to insert the new elements into the green area. And there are two conditions that can make this happen. Either because we're reaching the end. That means that element should be the minimum for the green area. Or the current is simply larger than or equal to the current element we're talking about. That means that is the right spot to insert, okay? So these are the only two conditions that's possible. So that's something I want you to think a little bit more carefully by yourself. Yes?
I think the reason he said 3 is because the first one could be false, the second one could be false, they both could be false.
Well, that's true, but I'm just trying to, yeah, basically I'll just talk about the two conditions. Either that is false or that is false. Yeah, I agree with you, yes. Okay, so that's just an aside for you to convince yourself why it is the case, but we'll see examples. So now let's think about over here. Basically, you can see that rather than going too much into the code, which means you can easily get lost, let's think about what this while loop would do. This while loop will simply just tell you where to stop to insert the new elements. And while you are trying to find the right spot, you shift everything to the right. That's what it is doing. Okay, let's try. Okay, what I will do is, let me just draw the array over here, and then to show you how it works. Okay, we got 3, 1, 4, and 2. Okay, and then we got the green one. The green is initially pointing to the I. So I is pointing to 1. That's I. Okay, let me just put it below. That's easier for you to see. This is I. And then what about J? J is simply assigned to I over here, right? So that means J is also pointing to the same spot over here. And then we're basically trying to check to see if AJ minus 1, what's AJ minus 1 in this case? 0, yes, I agree. But what about the elements at index 0? 3. In this case, it's simply just 3. And what's current? Current is 1. 3 larger than 1? Well, that's simply false, right? So, no, sorry, the 3 larger than 1 is actually true. Sorry about that. Yeah, sorry. That's why you're going to be careful, yeah. Make sure you teach somebody when you really understand, right? So, yes, that's actually simply true. When it is actually true, that means we'll go into the body of the loop and then try to do something. So here's a critical part. Because we know this condition simply is true, so we're going to execute this. What's going to happen? With the AJ, J is actually 1. That means A1 is assigned to A, J minus 1 would be 0, right? 1 minus 1. So A1 is assigned to A0. That means this part here, A1, is going to be assigned to A0. That means replace this part and move 3 over there. That's what it is doing. Okay? And then we do the J minus minus. So after that, J is going to be decremented from 1 into 0. Right? So that means J at line number 8 will be simply just 0. Okay, what does that mean? That means over here in line number 8, we know that J should really tell you where to insert that particular elements, whereas we have already shifted everything that's larger than current to the right. Okay, so now AJ is at the moment 0. A0 is assigned to current. Current we know has always been 1 over here. Okay, so that means this is going to be 1. So what have we done? What we have done was something like this. Basically, wrong color, sorry. 1 is basically the one that's already sorted, whereas the rest is simply not sorted, 3, 4, and 2. Okay? Shall we do just one more iteration? Just one more, very quickly, rather than the complete details. You can see we are just trying to make progress like selection sort, just the way we make progress, each step is different. Okay? Let's do one more very quickly. So what I can do now is, let me just go draw a separator over here. So now when we go back to the beginning of the for loop over here, let's say over here, I is now going to be 2. Okay? I is going to be 2. And then what about J? J is also going to be 2. 2 is going to be over here. Agree? Okay? So basically, I'm going to let you follow exactly the details over here, but what I would like to show you is how the array is going to look like and how we're going to deal with it. Let me draw the array over here and how we started with. How we started with is something like this. We have 1, 3, 4, and 2. Now think about which element are we trying to insert into the green area? 3 over here, right? It's actually 3 we're trying to insert into the green. Green has only one element, which contains 1. But now we're trying to see where should we insert 3 into. This case, we are lucky, right? Because 3 is already larger than or equal to 1. So that means we just stay there, and then we'll immediately exit from the while loop. That's what's going to happen. Okay? So that means after that, what we're going to get is 1 and 3 over here, unchanged, basically. But you should know how things work for the nested loop. And then 4 and 2, still the same. Okay? Guys, any question about insertion sort? Let me just give you a very quick hint. The reason that you can see moving from this array into this array, the contents don't really change. But conceptually, if you think about, we have expanded the green area by 1 element. The reason that they don't change was because you can see the element we are trying to insert into the green area is simply 3. And 3 is already larger than what you call the maximum element in the green. So that's why we don't have to change anything. There's no shift to be done. So that's why this remains the same. So 1 and 3. Okay? Yes? Say it again? When I is equal to 2, yes, we look at. Yes. When I is equal to 2, yes. That means we're looking at over here. You know what? Let me try to see this. We kind of went to 2, yeah. You know what? The diagram is getting a little bit messy over here. You know, how about this? I would say to save our time, what I would do is I'll try to recreate a diagram, and I will just show you the second iteration in the beginning of Wednesday. That'll be a little bit better. If I just mess around the diagram, it's going to make things worse. Okay, what I would do is the first iteration is like how we discussed over here. And now for the second iteration, let me just go over that with you in the beginning of Wednesday, after I create a new diagram to show you. Yes? Yeah. Yeah. You may swap it, that's fine, but basically the idea is eventually at the end you want to insert that to the right spot. But how you actually do it is completely up to you. It's just for this particular solution, we just shift, right? You can also do swap if you like. Not necessarily, because if you go all the way from the right to the left, for each either swap or shift, it's basically the same. For each, yeah, you still have to go over that much size of the array. Yeah. Okay, guys, so I would say at least understand until the end of the first iteration over here. What I will do on Wednesday, I will try to show you the second iteration in a little bit clearer picture. Okay, that's what I would do. Okay, but any question until now for insertion sort and selection sort before I just summarize them? Yes. Say that again?
Can you rephrase the first slide, like before the code?
Sure. You mean rephrase? You mean to summarize? I mean over here, right? Yeah. So very quickly, for selection sort, well, thinking this way, insertion sort and selection sort, both of them take n steps and correspond to the input size, how many elements you have in the array. But now, the most expensive operation for selection sort is the very first step, which means you're going to select the minimum from the red area, which is of size n. But on the other hand, the most expensive operation for insertion sort is at the very last step, in which case, over here, you're given basically already a sorted green area of size n minus 1. But now to insert this red element into it, you have to go, in the worst case, all the way to the beginning, right? That's why it will also take n minus 1. So if you add up the numbers together, it will turn out to be the same. Just the way you add them up is different. Yeah. All right, as I said, there might be more than one way for you to program this abstract idea. The code I show you over here is simply just one example. So you feel free to modify the code and make sure it still works and pass me the tests. Okay, any more questions? Okay, one more thing to talk about. If I give you something like this in the test, I want you to figure out the asymptotic upper bounds. How would you do it? Right? How would you do it? Well, you can forget about the fact that let's now wearing a different hat, right? Before we know abstractly how insertion sort and selection sort work, right? And then we trace the code. But now let's imagine this is simply just F, and this is simply just G. Let's say I give something like that to you. I want you to figure out asymptotic upper bounds for each one of them. How would you do it, right? The way you do it, I'll mention very quickly, is about to see the pattern for the loop counters, I and j, basically. They'll be much easier. Remember the simple example we did before, like a triangular sum, or simply find out the duplicates, right? Depending on the patterns. Let's just do one together. I'll leave the next one, the other one for you. If I look at this over here, you can see I is going to be from 0 until n minus 2. I is going to be from 0, 1, 2, all the way to n minus 2. Agree? Okay. Now what about for each value for I? What's going to be the value for j? J is going to be starting from I and then go all the way to n minus 1. Okay, so that means when I is equal to 0, what will be the value for j? It's going to be from 0, 1, all the way to n minus 1. Agree? And then what about when I is equal to 1 for the second iteration for the outer loop? That means j is going to be equal to 1. They'll go from 1 until n minus 1. So j is going to be 1 until n minus 1, and etc., right? You go all the way like this, and then for the last value for I, j is going to be from n minus 2 and then to n minus 1, like that. Okay, that's how how you observe the patterns for each iteration. Okay, now that's how you figure out the number of iterations for the body of the loop. But now let's have a look to see how they would look like. If you look at the body of the loop, there are two parts over here. First part is, if you look at this part over here, what's the asymptotic upper bounds for this line? Just for this line, for each iteration. Would it be constants, quadratic, cubic, or what would that be? Constants, all right? Basically, you can see there's no loop over here, just if conditional. So basically, you count the number of primitive operations, it would just be a constant. So for this part over here, it would just be just constant. Just big O of 1. Okay? And then this part over here, again, similarly, this part, which will simply do a swap between the two elements, right? That will also be big O of 1. Okay? And now this part over here, about the values for I and j. So for when I is equal to 0, we have m possible values for j. When I is equal to 1, we got m minus 1 possible values for j, for that many iterations. And finally, when I is equal to n minus 2, we got actually 2. And then for each iteration, we got exactly just 1, big O of 1 primitive operation to execute for the body of the loop, right? So that means we're going to have n plus n minus 1 plus all the way to 2. And then multiply by basically big O of 1. You know, let me just put it inside the big O so easier for you to see. So it's going to be big O of multiplied by just 1. I'll just annotate that for you. So this is the running time for each iteration, which is just over here. Okay? And then this one over here is the number of iterations you need aggregated together. Okay? So there's a number of iterations. Well, if you try that, what's gonna be the running time? Well, we know very well if you got a series like this, it's gonna be n squared. N squared plus multiplied by 1, just n squared. So eventually, it would just be big O of n squared. Make sense? Okay? And similar exercise for you for G. Okay, I'll leave that to you. In the test, given complicated code like this, I wouldn't ask you to really count the precise number of primitive operations. It's not very useful. I would say as long as you can show the TA or myself how you observe the patterns for loop counters over here and figure out the number of iterations, step number 1. And then to see for each iteration step, what will be the running time for your loop? In this case, the pink part, and also this part over here. So that will be just big O of 1. So if you multiply them together, you get quadratic. Okay. Questions about running time? Are we all right? Okay. Yeah, running time is a very important topic to be covered by lab test 2. I would say I'll give you some exercise a little bit later this week, give you some challenging one So be really ready for the lab test, right? You'd rather get some challenging one before the test rather than in the test, right? Okay, I'll give that to you. Maybe I'll give that on Wednesday. Okay, let's now move to another topic, which is not so mathematical. Okay, it's a different topic. Let's go back to classes and objects. So there is a topic called callbyvalue, which I would like to talk about. And after, one more thing before I move to callbyvalue. So if you look at the slides, everything that we have talked about already, so this is an exercise for you. I'll explain to you what's the nature of the exercise. Let's have a very quick look back to the iPad over here. You can see the way I describe the sorting for both insertion sort and selection sort. The way we grow the green area is from the left, and then from the very left, and then every time we simply grow the green area from the left by one element, right? Is it possible for you to implement insertion sort and selection sort in a different flavor from a different direction? What I meant was this. Let me show it to you conceptually. Let's say this is the array we have as the input. Initially, nothing has been sorted initially. But now, the way we want to grow the green area is a little bit different. Rather than growing the area from the left, we want to grow the green area from the right. That means after the first step, what I want to have conceptually is something like this. The green should be over here, and the pink should be over here. What kind of modification do you have to make for selection sort, conceptually? Exactly, right? Let's say we still want to sort in the ascending order, let's say. So now, what kind of modification, what's the most critical modification you have to make to a selection sort? Do you still have to select minimum? You should select the maximum, right? Because now, once you select the maximum from the whole pink area, it's guaranteed to be the maximum for the entire array. Okay, that's the modification. Okay, and what about insertion sort? Insertion sort is you still want to insert the green one into the green area over here, but now the way you insert into it, maybe from left to right, you have modified the while state condition a little bit. Okay, that's my hint to you. So this will be not so challenging exercise, I would say, if you want to improve your coding techniques, especially for nested loop. That's something I would suggest you try. Okay? And if you want to check your code with me, feel free to come by. Okay? I encourage you to do that. Okay, and then let's see what else to say about sorting. Okay, one more thing to mention. As we all agree, asymptotic upper bounds for insertion sort and selection sort is quadratic. How bad is that? If you think about the way the math work, selection sort, insertion sort, it is big O of n squared. What does that mean? If you try to sort 1,000 integers, what's the worst case? How many primitive operations do you need to execute? 1 million. 1 million primitive operations. Not to even mention if you got 1 million integers to sort, well, 1 million square primitive operation. You can see how fast it is going to grow. However, we deserve something better a little bit later in the course. I will try to at least talk about a particular sort. It's called merge sort. For your lab number 3, remember you're trying to use arrays.sort. That's exactly how they implement the arrays.sort, merge sort. It has to do something to do with recursion, which I'll try to show you a little bit later in the course. Okay? But now let me just give you some intuition. Merge sort is going to be much better. It's going to be big O of n log n. Okay? Why is it good? Well, why don't we try? If n is equal to 1,000, then how many primitive operations roughly do you need to execute? 3,000? 10,000, right? Well, let's say log is base 2. How about that? Okay, so that means 1,000 multiply log 2 base and then 1,000, right? So this is roughly 10. So you got 10,000. 10,000. which is much smaller than 1 million already. Let's do one more. What about when n is equal to a million? It's going to be 1 million. What's log 2, 1 million? Yeah, 20-ish, yeah, I agree, good. Yeah, it's like a 1,000 to the power of 2, yeah, exactly, very good. It's going to be 20K. You can see over here, you go from 1 million to 1 million square. He only go from 10K to 20K. That's why merge sort is definitely the way to go, rather than insertion sort, selection sort. But it's worth learning about the basic sorting to appreciate why something is more efficient. Yeah.
I was gonna say, why would we ever use the other two?
I would say, yeah, you can see it's really about like an input size you're talking about. If you're only implementing a very small database up to maybe 1,000 people or student records, I think selection sort, insertion sort is still okay. But if you talk about more industrial strength application, you've got a million things to sort, don't try insertion sort, selection sort, right? I would say it's really about the context you're talking about, yeah. But for you guys, a beginner, I would say insertion sort, selection sort is definitely worth learning, yeah. Many things you can learn from the 2 case studies. But as a promise, there's one missing puzzle I would like to go over in the beginning on Wednesday. For the second iteration for insertion sort, I'll do that on Wednesday. Okay, so now let's talk about aggregation composition. And before that, I want to talk about something called call by value. Basically, you have already learned about it when we did a review in week number 1. There's only one small detail I need to add to it, and then we'll do examples, and we'll do 2 or 3 examples, and that should be enough to understand the whole picture. Okay, let's now talk about it. Basically, the idea about call by value is you got to think about where you define the method and where you're using the method, okay? Let me just go to iPad right away, okay? We'll do 2 examples together. But let's try to understand the general architecture, the structure first. Remember we talked about caller, callee back in the exception lecture, right? Caller, callee, or caller is like a client. Callee, who provide the service, is more like the supplier, okay? So let me just use that naming convention over here. Let's say over here, let's just go over the structure very quickly, and I'll show you how you can instantiate that to the example. Let's say we have a supplier class over here, which provides a mutator method called M1. And then over here, we have a parameter, which is a par, and then the type is simply just T. How many possible types do we have in Java? How many categories of types? Primitive and reference, right? That's why we got 2 cases to consider. Very good. So now T here, make it completely general. T may be int, bool, char, or double, right? Like a primitive type. Or it can be any reference type, like a circle, or points, or utility, whatever. Okay, that's about the supplier side, and the T can be either primitive or reference type. On the other hand, we also got a client side, which is going to call the method from the supplier. Let's say we initialize a supplier object over here, just by calling the constructor here, and then we somehow initialize the argument value arg over here. Depending on what T is, if T is simply a primitive type, you can simply assign a value to it, right? You can say int arg equals 4, for example. But if there's a reference type, you have to use a new keyword to create the objects in the memory. Okay, we'll see both examples. But now the important thing is over here. When we try to call the method M1, we must have a context object. In this case, it's simply S. S is of type supplier, which support the method M1. And then we're passing this value over here, arg. Okay? So now I want you to focus on how we execute this line of code. That's the thing. What I said before in the week 1 review was simply like this. I said, given that we actually got the context object being S, and then we got M1 over here, that means we're talking about the execution for this method over here. And then the fact that we're passing a value called arg, we're going to replace every occurrence of par by arg, right? That's what we said before, right? So for example, I'm going to replace this by arg, and whatever occurrence of par over here, I'm going to replace that by arg, right? That's what we said. That's not wrong. But now I want to make it even more precise for you, even more precise. That's the nature of call by value. This is how you can think of it. When I say replace this par by arg, What I really meant by this is a simple assignments, like this. I simply say, before we try to execute line number 1 for the code of the method, there's some implicit assignment Java runtime does for you. You don't need to do that, but they do it for you, which is par assigns to arc. The way I get around with this is simply say replace every occurrence of par by arc. But it's basically to say assign the value of arc into par. Okay? Conceptually, that's how what happens. But now let's think about it a little bit more. If t is actually a primitive type, let's say integer, so what are we doing here? If you try to say I is assigned to j, both are integers, you basically copy the value of j into I, right? But what if t over here is a reference type? Are we copying the objects? We're copying something else. We're copying the address. That's how we make aliasing, right? That's basically back to our review lecture in the first week. Just keep this in mind, and then we'll see from the examples. Okay, so now the only thing that's new to you is whenever you're trying to call a method like this, you're basically doing these assignments under the hood. You don't have to do it, but Java runtime does it for you. And it is called callbyvalue. You call the method, and then whatever value the argument is going to be passed into the method. But let's see the example altogether. Okay, and then you will see why it's useful for your understanding. Case number 1. Let's say the t that we talk about here is simply just primitive. Make it easy. So now let's consider 2 classes over here. Let's say we have a class called circle, and then with an attribute called radius, and then we have a mutated method set radius, and then the parameter is simply just integer, which means it's primitive type. And then we simply say this.radius is assigned to par, right? So far so good? What about on the client side? On the client side, what we got is something like this. So we have circle user, and then we create a circle objects, and then we have an argument value arc is simply just 10, let's say, right? There's no keyword required. It's simply primitive type. And then we have this method call over here. Let me highlight a different color, like this. So now, how do we understand the execution of this method over here? How do we understand it? Okay? Let's think it this way. First of all, what we can do is we have an object called C, which is created over here. So C is pointing to a circle object in the memory. And then every circle has a radius attributes. Just put R. I'll put radius. And then it's simply a default constructor, which means the value will simply default just 0 to begin with. That's after this line. And then we got this integer arc 10, which means arc is like a box storing the value of 10, like that. And now what does it really mean when we try to make a method call like this, c.setRadius arc? So now the way to understand this is when you try to execute this method over here, rather than thinking like in the 1022 way, we simply par is going to be replaced by the value of arc, which is 10. That's how we thought about it. Let's be more precise how this actually happened. Okay? The way to think about this is implicitly, before you try to execute this block of code, before you do that, you basically got par is assigned to arc. You don't really see this in your Java code, it was just done for you at the runtime. So what that means is you got another variable here called par. And then you copy the value 10 over, so par is now 10. So now you don't have to do any replacement anymore, because now whenever you talk about par over here, you know what the value is, which is a copy of the arguments, 10. Okay, so that means it would just be 10 in this case. Guys, any questions about this? Okay, are we all fine? Okay, so now if we try to make the case a little bit different, let's consider the other case. Here we only talk about the t type being primitive. What if t is reference type? We're basically going to make some alias. We're copying just the address of the objects, But how is this going to happen? Okay, that's why we've got to be careful. Okay, let's go to the second one. Over here, basically the same circle example, but I'm going to change the parameter type a little bit. Rather than integer, let's put an object type over there. Okay, let's just review quickly. Over here, still got a circle class. I got the radius attributes. Let's say I got another constructor over here, which is going to have some initial value for the radius. And here I say this radius is the radius. No problem. And then I still got this mutator set radius, but now the parameter type, rather than being integer primitive, I'm going to make it circle, which is reference type. That's the difference. Okay? And then I still got par over here, and then I simply say this radius is assigned to par.radius. Okay, so far so good. That's about the supplier side change. I make it very similar so that you can compare the difference. Now let's go back to the user. So circle user is over here. Okay, and then we still create a new circle called C. Eventually we want to say C dot set radius. Eventually. Okay, but now how do we create argument value? Since the argument value now is going to be of reference type, so what I will do is I'll use a different color here. So say arc over here is going to be of type circle. So I'll say new circle 10. And then I'll simply pass the argument over here. Okay, that's a difference. But now let's see how the code will be executed. It's not going to be so much like what we have seen over here. A little bit different. Okay, let's see exactly how they're different. Principle is the same, but the runtime structure will be a little bit different. Overall, if we are trying to execute these 3 lines of code, how many objects do we have to create in the memory? 2, right? Well, it's easy to count. Just count how many new keywords we have, right? Easy. Good. Let's try. First of all, let's see over here. When we execute this line over here, C is going to point to a circle objects with attributes radius. And it's simply default constructor, which would just be 0. That's about C. What about arc? For arc, I'm going to use a different color here. I'm going to use maybe pink. For this line over here, it's just going to be a second object of type circle. So I'm going to have arc is going to be pointing to also a circle objects. And circle also got the radius attributes. And since we got 10 over here, we're going to execute this block of code. We're going to set it to be 10. Okay, so far so good? Now, here comes the most critical line. How is it going to happen if we try to execute this line over here? Okay, apparently, the context object is C of type circle. That means we're going to refer to the setRadius method in the circle class over here. So now, how do we pass the value for arc? That's the question, right? Don't worry too much, just follow the same principle. What we said before, the principle was, it's going to be par is assigned to arc. Just do that, okay? So that means over here, before we try to execute the block of code over here, you don't have to write it, it's going to be done for you at the runtime. It's going to be something like this. Par is assigned to arc. Call by value. But now this time, what's the value that's being copied? It's the address that is stored in arc that's being copied over to par. Okay? How do we change the diagram right now? Do we need to add a new object, or do we add a new arrow? New arrow, right? Should the arrow be pointing to the pink objects or the blue objects? The pink, right? Right? Think about this. When I say par is assigned to arc, I'm trying to copy whatever that is stored in arc, which is the address of some circle objects, which is the address for this object over here, right? Copy the address of this object into par. That means par is now going to point to this object over here. Agree? So now that means par and arc, they are aliasing to the same objects. Okay? So now we don't have to worry about replacing every occurrence of par just by arc. We don't have to do that anymore. Because now when you talk about par over here, it's basically just talk about the same object as referred to by arc. Let me do a little bit preview for you in the case of reference type. Question for you. Let me propose two kinds of changes to you. All I want to know is the pink objects going to be changed or not? That's all my question. Okay, this is pink objects, okay? I'm going to write my question over here. Is the pink objects going to be changed? Okay, yes or no? Okay, let's try the first one. The first one, let's say I add one more line to the set radius method, just over here. Okay? What if I say par over here is simply assigned to new circle and 20? Is this blue line I just added going to change the pink objects or not? What? Yeah, sure. Okay. What's the question? The question is as follows. I'm trying to add one line over here, which is par is assigned to new circle 20, right? Is this new line here going to modify the pink objects, which is over here? Is it going to modify that in any extent? No, right? What's going to happen here? What's going to happen is basically we're saying that par, rather than pointing to the pink objects, is just going to point to another object, right? Circle over here, and then with the radius, simply 20. That's what's going to happen. Okay with that? Which means if I try to reassign the par, it's not going to affect the original pink objects. Second change. Okay, if I simply say par is assigned to new circle, okay, this answer is no. Okay, what about second one? The second one is like this. If I say par dot set radius -1, second change. So rather than do it in the reassignments to the reference, I'm trying to use that reference there to call some mutated method. It will change? You think so? Yep, exactly. Everybody agree? Over here, if I say par does set radius -1, so par is basically still pointing to this. I'm talking about second change, right? So par used to be pointing to over here, and then when we say par does set radius -1, we're basically talking about this same object over here and change that into -1. In that way, we can modify the objects. Okay, the answer is yes. So these two changes are really the most important ones for you to distinguish between when you talk about call by value for reference type. I will give you another example, a little bit more complicated to show you. Here's a summary of changes. When you have a call by value for reference type, there are two kinds of changes you can make to your parameter. Either you can make a reassignment for the parameter, in which case you simply reassign the parameter into a new object, in which case the original object is unaffected. That's the first kind of change. The second kind of change is you're basically using the address value over here to make a method call to modify whatever object is being aliased between arc and par. So that means this change will be visible to both par and arc. Okay? Again, that's the aliasing that we talk about. So two kinds of changes. You should know both very well. Okay? Any questions until now for this between these two simple examples before I show you some slightly more complicated ones, slightly. Okay, are we okay? Okay, let's go over these examples here. Okay, I think again, the most important line for you to understand today for call by value is whenever you do this, it's basically this implicit assignment that's done for you. Again, you don't write this assignment by yourself. It's done for you. Okay? And then all the rest I've already said. So what I would like to do is I would like to go over examples with you.
So now again, call by value, call by reference. Okay. Now let's go over the code together. Okay. Now first of all, we have a class called points. We have a point class over here. Oh, actually, that would be better. We have a point class. We got attributes x and y of type integer. And then we have a constructor over here, which initializes x and y. We also got another mutator over here, which will change the value for y, and also another method here, which will change the value for x, okay, for point. Let's now consider different test cases, okay? Let's go over one by one. Let's just have a look at this test over here, okay? So the method I would like you to focus on for this particular slide would be this one here. I'll highlight it. Okay, just this one here. Reassign int. I just found that this example here doesn't really use point. I'm not too sure why I included it. Yeah, anyway, forget about points. Point is actually not necessary in this example here. Okay, sorry about that. So now we do have over here, util class over here, and then we have reassign int. And the parameter type over here is of type integer, right? That's the first case we talk about, okay? And then we're going to have simply reassign j into j plus 1. Okay, now let's see what's going to happen over here. Let's have a look at the test and see what it is trying to express. We create a new util object over here, okay? New util. And then we have argument type, which is integer. I is of type 10, value 10. That means I is 10 over here. And now, just focus on this value over here, this method call. When I say u.reassign int I, let me ask you this question over here. If I try to print out the value for I before this call, what's going to be the value for I? 10, that one is easy, right? That's easy, just 10. Initialize that to be 10. But now, if I try to execute this method here with I being the input arguments, and somehow the method over here intends to reassign j, which means implicitly we should have something like a j is assigned to I, right? That's what I said before, implicitly. Is this method here going to increment I, which was initially 10 to 11? Okay, yes, no? Okay, I heard some no, which means there might be no, that's good. But if I heard yes, you may still have some confusion there. Let's see this. As soon as I try to call this method over here, what's going to happen is like this. J is going to be the parameter over here. And then it's going to copy the value from I, which is 10. So now we've got two copies of the value 10. So now, as soon as I say J is assigned to J plus 1, which box I'm trying to change? The J. And the original I is unaffected. Okay, so that means you cannot modify the value that is stored in the arguments directly. Yes?
So if you change I, would have to be a return method?
If you, okay, that's a good question. The question is, what if I do want to change the value for I over here? Let's say I want to change it so that it is used to be 10, but now maybe after that it becomes 11. The answer to your question is, in Java, you cannot. You cannot, because remember, call by value. Every time for the method over here, as soon as you see the value for j, j is already a separate copy of the value for I over here. So whenever you modify, it's going to be modifying this separate copy. If you really want to do something like this, you can do it in C, the C programming language, which means you can pass the address of that particular integer variable rather than the value. But that's out of the scope for this course. Okay? Guys, are we okay with this simple scenario? Okay, right? Let's do very quickly the next one. Okay? The next one over here, again, so now let's have a look at the point. Now point is relevant. Okay? Again, we know how the point works. Now I want you to look at this method over here. Reassign ref. It's basically the first kind of change I mentioned before. Now, if I say Q over here, and then, which is a parameter, I say Q is reassigned to MP, What's MP? MP over here is simply a new point objects. Okay, like that. That's basically the method. So now I want you to look at the caller side. Okay, there's a test method over here. Let's have a look at this. We simply got some U objects here, so we can call U.reassign ref P. Okay, and then what's P? P is simply over here. So P is just a new object over here. Let's have a look. P is pointing to a point object over here from line number 4. And then X is going to be 3 and Y is going to be 4. Okay, so now I have a question for you. When we try to make this method call, what's going to happen? Basically, implicitly, because of call by value, before this, we're going to say Q is assigned to P, right? That means Q being the parameter is going to be pointing to the same object alias. And now, it seems like the intention for this method here is to change the address for Q, right? Because of Q is reassigned to MP. Now, my question for you, if you compare the address for P before and after this method call here, is the address going to be the same or different? Same, right? Because whatever we are changing is not the address for P. We're only changing Q into something else over here, which is going to be a new point over here. And then we got X and Y being 6 and 8. Okay, that's really, really important for you to see. Okay, now the reason that you can see that I got some intermediate variable over here is simply to capture the value for the address before